Here we consider a car taking a turn around a banked curve, such as an on-ramp onto a highway, or the curve around a racetrack where the road is tilted, enabling you to take that turn at a higher speed than you safely could if the ground was flat. So here's a side view of our banked curve. We've got the vehicle driving out of the page like that, and here's the vertical direction, and here is the center of the circular arc that the car is driving around. So it's driving sort of out of the page and turning to its left. So this would be the radius of the circular arc the car is moving on right there. And the most important step beyond getting our free body diagram right, the most important step here is AAA, align your axes with the acceleration. If we want our car to be taking this turn without sliding up or down the ramp, then the acceleration will be only in our radial direction, the negative radial direction. We'll have our centripetal acceleration. That's what's turning the car, allowing it to make that left-hand turn around the ramp. But we will have no acceleration in the vertical direction. And that way the car does not slide up or down the ramp. And so, although normally on a ramp, if we've got a box or something sliding up or down it, normally on a ramp we would take our XY axes and tilt them. So we have an axis lined up with the ramp itself. We would tilt our axes. We do that only when you're accelerating up or down the ramp. But in this case, we want to align our axis with the acceleration, and our acceleration is in the negative radial direction. So we do not tilt the axes here. We stick with a radial axis pointing straight out from the center of the circular arc over here. So a radial axis that way. And then a vertical axis, we'll call it the Z direction this way, our K-hat axis, like that. So we'll have radial and vertical axes, not tilted axes. That's the whole key to successfully analyzing the banked curve. And so, having chosen these axes to align them with our radial acceleration, we recognize that the force that we have to break into components is the force of the normal force. The normal force, that's the one that's not aligned with either axis. Gravity here is aligned with our z-axis. So, okay, making the normal force the hypotenuse of a right triangle with one leg parallel to our z-axis and one leg parallel to our r-axis. Let's draw in those legs. We recognize right away that the z component of the normal force must be balancing our force of gravity so that the vehicle is not accelerating in the vertical direction. The only net force will be this radial component right here of the normal force pointing in towards the center of the circle, curving the path of the car. From a bit of geometry here, check your angles. We can recognize that this angle here must be congruent to the ramp angle down here. Okay, so those are our congruent angles. And we can now set up Newton's second law. So in our z direction, sum of forces in the z direction, we have Fnz and the force of gravity, and we know that those balance. Fnz we can express as Fn cosine theta. So Fn cos theta equals mg. Then in the radial direction, sum of the forces in the radial direction over the mass, we only have that radial component of the normal force, that inward radial, negative radial, centripetal component there, so minus Fnr. From our trig, we can see that this is Fn sine theta, that side, so minus Fn sine theta over m. And then, of course, we set that equal to negative v squared over r for our radial acceleration. And those are the two equations we need. What we're able to solve for here is the speed at which it is possible to take this turn without the aid of friction. So no friction was present in this FBD. Frictionless ramp, say an icy ramp or a ramp where you're taking the turn just right so you don't need any friction. There appears to be one and only one special speed at which that's possible. One speed at which you can take this turn on a frictionless ramp without sliding up or down the ramp. So there's one and only one safe speed to do it. We can tell there's only one solution because everything else in here is a constant. This normal force, that normal force must be the same. So between these two equations, if we eliminate the normal force, we can solve for our speed. Let's do just that. Okay, so this equation says that the normal force is equal to mg over cos theta. So here in this equation, if I multiply through by minus 1 to get rid of the minus signs, I'm going to substitute in for that normal force right there, mg over cos theta. So subbing in for our normal force right here, mg over cos theta, that gets us here. So here is our mg over cos theta, that's our normal force, times the sine theta over mass. And then we have mass canceling out there and there. And finish solving for v just by multiplying both sides by r and then taking the square root. Oh, one more thing. I have sine theta over cosine theta there. So just recall your trig identity that sine over cosine is equivalent to tangent theta. So we'll replace sine over cosine with tangent, and we will have g times tan theta times r square rooted. That's our result right here. The one and only one safe speed at which to take that turn without sliding up or down the ramp. So if you're going faster than this, we know, of course, if you're going too fast around that curve, you're going to tend to slide up the ramp as you take it. Going around too fast, you'll start down here and sort of slide up the ramp, maybe launch off the top edge. If you're going slower than this, we know that's a problem also. If you're going too slow around the ramp, you'll tend to slide down the ramp. So this is also known as the critical speed. The one and only one safe speed to take a ramp of inclined at angle theta with a radius of curvature r, the one and only one safe speed to take it without the aid of any friction whatsoever.